Welcome everyone to the San Diego Kotlin user group. Today we have Jack presenting on functional reactive streaming with Kotlin Flow. Thank you for joining and offering to present today, Jack. Take it away.
Thank you. Yeah, so yep, like Ian said, we're talking about functional reactive streaming this month. And if you're not familiar, functional reactive streaming is kind of like, it's not really an API, it's like a high level architecture that is that is a reactive manifesto that basically describes a way of designing applications, and people have made libraries in various languages and platforms that basically try to conform to this architecture. In Kotlin, the Kotlin standard library comes with one. I guess it's not standard library, it's a coroutine library. It comes with one. It's called Kotlin Flow, and we'll be talking about that today. I'm not sure how familiar everyone is with just functional reactive streaming in general or Kotlin Flow specifically. So I wanted to start with a word cloud, like basically where you can just type in words that you associate with either functional reactive streaming or Kotlin Flow through chat. You can type as many words as you want, but only the last three will show up. So I will show you, for instance, I can do, for instance, like Kotlin and Flow, and it will pop up. Yep, sounds good. So
Oh, yeah.
And I was going to say, you do not have to try to come up with original words. So if you see a word up there that you really like, you can, type it in. Like, for instance, I see Andy had subscribers. I'm going to do subscriber again. And it will just be bigger. So it's like basically more votes for it. So it's bigger. So yeah. So anyway, so I think that I think that makes sense as what I would think most people would associate with functional reactive streaming in general. But like coroutines, I think it's very Kotlin specific. Well, not really Kotlin specific, but at least it is in Kotlin. But yeah, so what is functional reactive streaming though? And just really quickly, I want to give an introduction of it. Just those three words kind of says it all, right? It's like functional, it's reactive, and it's streaming, which functional basically means it's based on functional programming principles. So it is, and that to me is like the safety component of it. It builds on things like immutability, pure functions to help you write safer software. It's reactive, so it's built on an asynchronous architecture. We'll talk about that a little bit more, but basically the idea here is more efficiency, like being efficient with your what I call execution resources, which is, I guess, just a fancy word for threads. So it's just being efficient with threads, so that because threads are pretty memory heavy, it in turn it's efficient with memory. And streaming basically means it models your application's inputs and output events as streams of messages. So it's a stream of messages that you process. So functional, we'll go into each of this in more detail. So functional, the idea of functional programming is it's built around immutability, around pure functions that like a function's output should be driven purely by its input. It should not be, consuming stuff from immutable state from the global scope or anything like that. And in functional reactive streaming, you'll find that you work on streams very much as though you are working on a Kotlin collection in a functional manner. So using things like map, flat map, filter. And the idea is, as long as you also, again, the platform is functionally pure. And as long as you also provide functions that are pure, your application should be pure as well. Error handling, typically you do not throw exceptions in flows. Instead, you either return a discriminated union like Kotlin's result, or like something in arrow, or you can also do things like I want to return, if there's an error, I just want to return null. Because Kotlin's null safety is really good, you can do that, right? So instead of, like, let's say I may return a string, or there may be an error, I'll just return null. And Kotlin Flow has tools to help you work like that. I do want to mention, of course, it's not a silver bullet. First of all, functional programming doesn't solve all problems. also on top of that, Kotlin isn't strictly a purely functional language, right? It's a hybrid OO functional language. So it encourages functional principles, right? Like it has data classes to encourage immutability. But if you, for instance, you come from a Java world and you're like, no, I like my OO, I like my mutable state, I want to just use Java beans and I want to use setters and getters and mutable state everywhere. The Kotlin code is going to compile. You can do it. In all likeliness, your Flow program will run fine. But when you run into problems, you might have a harder time tracking it down because, you know, like an object state has changed since it was created. And you know, those are the kind of things that functional programming solves, that it's up to you to use. Reactive. I always thought the word reactive was a little bit weird, so I had to look into it, and I found that it's based on the reactor design pattern that I think actually existed as far back as 1995. I always thought of reactive as something that was popularized by the unexpected success of server-side JavaScript. I feel like around the time Node came out with server-side JavaScript, like the people thought that the way to scale up an application to support thousands of users is to use more threads, right? And this is true, like even today, like if you look at something like Tomcat, like a servlet engine that was popular at the time, like today, if you look at it, the default configuration for the Tomcat thread pool is 200 threads. And it's like basically saying it's 200 threads based on the assumption that you're running on a 16-core machine. So if you think about that, like, you know, 16-core machines really mean only 16 threads can be active at the time. Tomcat is basically assuming that your threads are going to be only 8% of the time busy, like 92% of the time it's going to be sitting there doing nothing. So which is, it turns out, we, you know, initially like it seemed like a good idea, but people started to realize that actually spinning up lots of threads actually means spinning up lots of using up lots of memory, because each thread can be megabytes, sometimes multiple megabytes, because like the entire stack of your function lives on the thread. So reactive is where people started to realize, oh, maybe more threads isn't better. And the idea is to try and minimize the thread to just the degree of parallelism needed. So if you have a 4-core machine, in theory, you should not need more than 4 threads. But for that to work, you should write functions that are non-blocking, right? So basically in Kotlin, that means using suspending functions, not using things like JDBC that does blocking IO. But having said that, again, this is one of those things that it is up to the programmer to do that. Like, so if they don't realize they're supposed to not block, like suspend when they're doing long running IO, or they don't realize they can put it on an IO dispatcher, then you may ending up with inefficiencies, and you're not really getting the full efficiency benefits of doing things this way. Finally, streaming. Streaming is really the thing that I'm going to go into a lot for the rest of the slides. But just really quickly, you model your application events as streams of messages. And what a stream is think of it, it's like a collection, but think of it as an iterator of messages of immutable objects. But one key difference is when iterator is usually based on a collection where everything fits in memory, everything is available right at the beginning. A stream, like the elements actually like basically materialize kind of asynchronously during runtime. So you get an element, you process it. The next element may come immediately after, or it may come, who knows, minutes later, hours later, days later. So, but all of that basically, and so streams can also be infinite, but that's okay because it doesn't all have to fit in memory, and it's processed lazily on demand and possibly concurrently, so that there are some basically tuning you can do. And the operators, as I mentioned earlier, is very much, and that's where the functional work comes in, based on operators like map, filter, flat map that you are familiar with from collections. They are the foundation of, you know, functional reactive streaming. So I will go into detail on operators next. I'm not going to go through all of them. There's about 40 or 50 of them in Kotlin Flow, I think. I want to say about 30 of them that are kind of standard, that's available in all functional reactive streaming implementations, like RX Swift, combined from Swift, Akka streams. But I will talk about 7 or 8 that I think are really, you know, common and useful to know. I do want to mention that because functional reactive streaming isn't really an API, every implementation is a little bit different. So Kotlin, like I said, because it is so null safe, and well, null safe is very, very core to Kotlin. They also have like functions like map not null, filter not null, which is not really part of other reactive, functional reactive streaming libraries in other languages. So the first one I want to talk about is map. And I think if you're familiar with collections, you probably know what this is. A map on a flow takes a function from the input type, basically the type of the element of the flow. And then it transforms it into a different thing. And then it produces an output flow that basically has the transformed values. Right, and you can see this in the animation on the right here, where I'm basically, the input flow is the thing on the left. It is an infinite stream of integers, start counting from 0, although basically infinite, so forever. In theory, I guess it will overflow at some point. But you'll see that the map call takes an anonymous closure where it's multiplying the value by 2 and converting it to a long. And I'm doing long intentionally to show that the map's input and output types do not have to be the same type. So it can be integer on input, it could be a string on the output, it could be anything. In this case, and I'm also demonstrating through the animation that if it's circle, it's an integer, if it's a square, it's a long. Right. If you want to look at the actual code, it looks like this. The first 5 lines you're going to see a lot because all about 7 or 8 examples I'm showing will use that as the input. But basically what it is saying is it is starting from 0, adding 1 each time. And it basically waits 2 seconds, emit a value, waits 2 seconds, emit a value. So 0, wait 2 seconds, 1, 2, 3. The map function you see here is basically the same thing that you see in the diagram, multiply the number by 2. The collect I'll talk about later, but it's based on the idea that flows are cold. So basically, when you create a flow, it does not run. It just sits there. It's ready to run. It knows what it needs to do when it runs, but it doesn't actually run until you call collect on it. And I'll just say you call collect on it, but there are actually a number of functions that are called terminal functions that they will all trigger, get the flow to start running, but collect is the most common one. One thing I'd like to talk about with these things is like the properties of the map function. Like what you can think about, like what you know is always true of flows when you're working with a map function. And 2 of these are that the input and output flow will always be the same size. So if you have an input that is infinite, the output will also be infinite. If the input has 10 elements, output will also have 10 elements. And when I say infinite, as you know, it's not truly infinite, right? It's only infinite if the program runs forever. It will basically, at some point, the program will probably shut down or die. So what I mean there is, if there has been like 10 elements so far, 20 elements so far, there will also be 20 elements on the output side, or at least maybe 19, right? 1 fewer, maybe the latest one is still calculating, but it should always be the same size. The other thing I want to mention is the output type based on the input type. The output type can be anything. It is not driven by the input type. So if the input type is an integer, output can be anything. It's determined purely by the transformation function. So whatever the function returns. Next operator I want to talk about, also a fairly common one, is filter. Filter takes a function that takes, again, all the functions will take as at least one of the parameters, the flows value. And in this case, it returns a Boolean. So it's a predicate, and the output is basically, if the predicate holds, it goes in the output flow. If not, it doesn't. In this example, the filter takes an anonymous closure that returns true for even values, right? So it modulo 2 equals 0. So you'll see on the output side only even numbers. So really common, and the code looks like this. Again, the first 5 lines you'll find is very similar. It's just an infinite sequence, an infinite flow of integers, 1 every 2 seconds. The filter method looks basically exactly like it. You'll see that this is a common thing. I just want to make sure that you realize that the code is exactly as I show you. There's nothing special there. Properties, the output size is never larger than the input because filter can only remove stuff. It cannot add stuff to it. So if your input is empty, the output will also be empty. If the input is 10 elements, the output can be empty, can be up to 10 elements, depending on how the filter is. If the filter basically blocks everything that's empty, if it's always returns true, then it's the same size, or it's somewhere in between, as you see here. The output type will always be the same as the input type. So in this case, left side and right side are both circles. You cannot turn a circle into a square because filter basically passes the same values through. Next one is take. And take is a useful tool for if you have an infinite flow, because flows can be infinite. It's useful for converting a flow from being infinite to a finite flow. And there's another variant, at least, of the take method called the take while, which takes a predicate. But the idea is it takes up to 10 elements in this example when I say take 10. So and again, when I say up to, because if the input flow has fewer than 10 elements, you're not going to get an exception. It just means you get that number. Yep. So this is what the code looks like. Take 10 and then collect. The output is always going to be finite with a take or a take while, and no larger than the input. And the output type, again, similar to filter, is always the same type as input because it is not doing any form of transformation. It is just limiting what goes through. The next ones I want to talk about, I'm actually not going to go to the slide just yet, but I want to talk about flat map next. And I think everyone is familiar with flat map on collections. If not, I'll describe it briefly just in case you're not. Maybe I'm not sure if everyone is how comfortable everyone is with Kotlin collections. But a flat map is like a map, except it takes a function that it takes an input that is the type of the input or of the collection. So like if it's a collection of strings, so the flat map would take a function that takes string as an input. Instead of producing the output directly, it produces a collection of the output. Right. So, and what that means is if you take the function and apply to a map, what you end up with is a collection of whatever output type is. Because you don't want that and you want to flatten it, that's why it's called a flat map, where once you have a collection of outputs, it flattens it back to a single flat collection. Right. So that's what a flat map is in collections. In flows, though, there is one extra dimension we have to consider, which is time. Because flows can be infinite, flows can, the elements can show up at any time. So what that means is so flat map in flow, first of all, instead of returning a collection of the output, returns a flow of the output. And that flow can potentially be infinite. It can be the case where the first element produces a flow, second element then produces another flow. But because of the timing is all messed up, like the second flow actually starts producing elements before the first element. Because of that, so all of this is just for me to say that in flow and functional reactive streaming in general, there are multiple versions of flat map. In Kotlin, there's 3. I'm only going to talk about 2 of them, but the 3 are flat map merge, flat map concat, and flat map latest. I'll briefly describe them and then I'll show you the animation. Flat map merge basically means flat map first and then merge concurrently. So all the output flows can start producing data at the same time. Flat map concat means if order matters, then you use flat map concat where it's serialized. So we process the first element first, and then after that we process the second and third. And this also means that if the first element's output is an infinite flow, you never see the second element's output. Flat map latest means I'll process the first one first until the second input comes. Then I discard the first one. I don't care about that anymore, and I'll just do the next. I will not talk about flat map latest because it is fairly straightforward, and I don't really have time to talk about every single element, but hopefully this gives you a good idea of what it is. So flat map merge, like I said, is a flat map, but where it is flattening concurrently. So all the outputs will basically be jumbled up. And so let me talk about this example, right? Flat map merge takes an anonymous closure that returns a flow, and this flow just emits the value itself, but converted to a long. So it'll be square boxes on the outside. Wait 3 seconds and emits again the same number again as a box. So when you run it, you'll see it looks like this. So 0 is input, 0 comes out. 3 seconds later, another 0 comes out. But before that, 1 is already here and 1 comes out. And 3 seconds later, 1, 2. So I'll leave this running for a little bit if you want to try and follow. Actually, let me show you the code real quick. Again, the code is really just the same. So the same input, the output is basically, flat map merge, emit a value, wait 3 seconds, emit another value, collect. I'll let you watch the code a little bit, but in terms of the properties, I'll talk about that a little bit. That with flat map, you really cannot, like map, if the input is a certain size, the output will be the same size. With flat map, you cannot say the same thing about it because the output could be a bunch of empty flows that gets flattened, so the output could be completely empty, or each element could produce any number of outputs. So you really do not know. The only thing you really know is that the input is empty, then the output will also be empty because you cannot just create something out of nothing. And the output type can be anything.
Right. So,
you have questions?
Yeah. Just, I think maybe I might be misremembering, but in the previous examples, you had a flow and then like the map or the filter function was afterwards. And in here, the flow is within the flat map merge function. And so, yeah, that would seem to, because you can do, you're doing 2 emittings. Here. Yeah.
It's a little bit weird because, there's the flow on the inside, but then they all get combined into an outer flow. And what you're saying is the outer flow, which is all the inner flows merged together.
Right.
Okay. Question, how is this different from the lazy version of flat map? I actually do not know what the lazy version of flat map is. So I can't say. I mean, if it's a flat map on an iterator, typically it's still all the data is still there. And maybe if I understand correctly, perhaps the lazy version of flat map. Again, I don't really know what that means in Kotlin or really anywhere. Like if it's like, say, for an iterator where iterator values are lazily applied, then maybe it's more like flat map concat, because I believe flat map on a collection side will always maintain the order. So let's talk about flat map concat next, though, because I think there's also one extra interesting thing that I want to talk about there. With flat map concat, I basically implemented the function exactly the same as with flat map merge so that you can see the difference. So flow in this case, like same thing, emit the same value as a long, wait 3 seconds, emit the same value again. But this time when you run it, I want you to notice something special too, though, which is you'll notice 0 comes out. So the output is 0, wait 3 seconds, another 0. But you notice that the 1 actually does not appear on the input stream until, like, you'll notice they are spaced further apart than previous ones. And in this case, it's actually 5 seconds apart now. And this is a thing called like demand. Like basically, if there is no demand on the output side, if the output doesn't need a value from the input doesn't produce it. It's referred to as demand, and I think of it as how back pressure is implemented.
Back pressure.
So yeah. So this is great, right? This is amazing because if you think about it, this means, like, in this case, I'm just producing numbers. I'm just generating numbers, which isn't computationally expensive by any means. But imagine if this was an expensive operation. It means you're not really wasting time calculating until it's actually needed. Also, if let's say if it's making a HTTP request, you're not making requests unnecessarily. So that is, I think, the first time where we're starting to see back pressure there, where it's actually the input side will actually slow down for the output side, which is kind of trippy if you think about it, because if you're used to thinking about, okay, the input is just doing things, it doesn't care about output, it just keeps going, and then if the output is ready, it will do something with it. If not, whatever, it's there. But actually, like this is how Flow works, where it will push back and the input knows not to produce an output, a value until the output needs it. So that's pretty cool, I think. Next one, fold. I think people, if you're used to Kotlin collections, you probably do know what a fold is. But I will again explain just in case someone is new to it. The idea is this is a little bit harder to explain, but hopefully the example will make it clearer. Another similar one to is reduce. So if you know reduce, fold is very similar to a reduce. The difference is fold, you always start with an initial, you give it an initial value, and the initial value can be a different type from the type of the flow. And I'll actually show you that here. And then it takes as input an initial value and what I call a combining function. So a function that combines the accumulated value, which starts with the initial value, and the next element in the flow. And eventually it combines all of them, and eventually it produces one output. So one key thing to note is fold is a terminating operation. The output is actually not another flow, but an actual single value. Which makes me realize my diagram is actually wrong here. There shouldn't be a vertical line here because the vertical line here implies it's a flow. I should remove that. But so again, in this case, and one thing I want to show you too is, I'll show you the code. This is the one where the input flow is different, where instead of generating a number infinitely, this only generates 10 values. And the reason is because fold is what's called a terminal operator. And because it's a terminal operator here, also you'll notice there is no dot collect at the end. It doesn't need a dot collect to run. Like it itself causes the flow to run. Mm. So fold in this case, so it takes 0 as the initial value. And notice 0 is a long instead of an integer. It takes a function that takes the accumulator, which is a long, and next, which is an integer. And in this case, just simply adds the two together. And because this is Kotlin, you don't have to it will automatically upcast both because you're adding a long to an integer, automatically turns it into a long. Key thing I want to mention, output is a single element. It is not a flow. And also the danger with doing things like this is if you didn't realize that the flow is infinite and you do a fold on it, you will never get an output. It will run forever.
Right.
So in this case, the numbers are just added together. You start with 0 as the initial value, and I think you add 0 to it, and you add 1 to it, up to 9, and that's 45. An interesting one related. So I guess the question you might have is, what if you have an infinite flow and you want to do something similar, and you're interested in the fold output, like the combination output of each step? And for that, you have what's called the running fold. Running fold is an interesting one because it is a term that Kotlin, so it exists in functional programming, and it's called scan in functional programming. And Kotlin Flow has scan also, but I think the term is just unintuitive. So Kotlin decided to create an alias for it called running flow. So both of these functions do exactly the same thing. You'll notice that the signature is exactly like fold, with the exception that you'll notice that the first box is gray, and this is the initial value. So initially produce an initial value of 0, add 0 to it, that's 0, add 1 to it, you get 1, add 2 to the value, you get 3, add 3, you get 6. So you'll see, again, this is like a running total, and that's why it's called a running fold, right? So either like running total or running product or running whatever. But you get the value of each step. And because it's a running fold, it is okay for the input stream to be infinite.
Yeah.
Make sense? Any questions? This is what the code looks like. At this point, it's literally, the same value, the same code as you see in the diagram. Something interesting about the properties here is that the output in this case will always have one more element than the input, because it is the input, all the input values plus that initial value.
Yeah, sure.
And output type can be anything. It is really determined by the initial value and also the function's output. I will actually show you an example where in my I have a sample application, flow application written as well, and I'll show you an example where the initial value, so the accumulated value, is a complex type. Finally, I want to talk about collect, which is another terminal operation that you've seen multiple times. Like I said, you need to call collect for the flow to actually run. So that's because flows by default are cold. So when you create a flow, it doesn't actually do anything. It has the code, it knows what it needs to do when you run it, but it doesn't actually run. So it's not consuming any threads, it's not consuming any processing resources. And it starts running. I say when you call collect, but really what it is when you call a terminal operation. For is a terminal operation, first, last, those are all terminal operations because they return a single value out of the flow. So collect, that takes a function. It's called a flow collector, but you can implement it as a function because there's a, I think, like SAM conversion. It's a pretty useful terminal operator, and it's the most general one. So like full is implemented in terms of a collect, or this form of the collect. Collect also is implemented in this form as the collect. They're all, and what it does is if you want to run it and you just want to do with each output, you just want to do something with it. In this case, I'm just printing it to console, but you could, like make a HTTP call with it or whatever. This is what you would use. I think it is important to talk about the difference between terminal and non-terminal operators. So I just wanted to have a slide on it. Key thing to note, terminal operators will run the flow, while non-terminal operators are lazily applied to it. So when you have a flow and you just say, I want to map by multiplying the number by 2, you're not actually doing it right then. It just means when you run it, I will multiply the number by 2. A terminal operator can return anything. So it can return another flow potentially, but most people probably would not do that. But it can return any non-flow types. Whereas non-terminal operators like map will always return another flow. Filter will always return another flow. And finally, key point also, terminal operators suspend. And they have to suspend because, flows can run forever. It can run. You do not know ahead of time how long it will run. So a terminal operator has to suspend because it is running the flow. Whereas non-terminal operators do not run the flow and therefore it does not suspend. It just creates a new flow that when executed will do a specific thing. Any questions on operators? Okay, if not, let's get into the example application that and again, I made the example application based on that I chose those operators because they were used in the example applications, is what I'm saying. So the example application I'm building will be a word cloud, as you saw in the beginning. So we'll look at, so we've seen how operators work in isolation. So we'll look at how we hook them up together, compose them to build a full application. And I think a word cloud is cool because it is simple enough to understand, but it's also not trivial. It's not just a hello world application, it's just a single flow. So, so when you start a flow, you basically need to start with a source flow. And in our case, the source event messages are Zoom chat messages. And you can see basically the Zoom chat messages show up on screen here. So the most recent one is on top. So it was in to everyone, coroutines. It was me. Then before that's me sending. So, and I can do, I can send a message here now, like, scalable, and it should show up here shortly, right? The first thing you do with the message is, I show you the code. So one thing I do want to mention, I did not need to do this, but I did it because for reasons you'll see later. The input flow can go from Zoom chat messages straight into my application, but I chose to go through Kafka. So again, the Zoom chat messages are being collected and sent to Kafka, and it's being read from Kafka, and this is the code that does it. So it's creating a flow of chat messages by reading from Kafka. So this is Kafka code. I will point out the important parts, but you create when you read from Kafka, you call it a receiver. And so you create a receiver setting reading from localhost 1992. I just hard coded it here. Kafka stores key value pairs. So in this case, the key we really don't care about for the purpose of the application. We kind of do, but I'll talk about that later. But we just deserialize it as string. And the value is a JSON object. So deserialize and then decode it into a chat message object, which has what you saw in the diagram, sender, receiver, and text. Group ID I'll talk about later. We don't really need to know. And once you create the settings, you just create a Kafka receiver that receives from this is the topic. So this is the Kafka topic that contains the chat messages. Map extracting only the value because, like I said, we don't really care about the key. And then sharing is a concept in Flow where it just allows you to, in case multiple people need to read from the Kafka topic, it is reading from this shared flow rather than everyone reading from Kafka independently. So flow of chat message, this is what a chat message looks like. There's a sender, there's a recipient, there's text. Next step is normalizing. So you apply a map operation. And if you're not familiar, Kotlin, colon is basically how you reference a function. So I've got a function called normalized text. And we are mapping by applying normalized text to every chat message we have. And we are extracting, we're only interested in the sender. We don't really care about the recipient, who is always everyone. And the text, which is normalized. And you'll notice, for instance, Ian's message coroutines has a capital C and it's lowercase here. I'll show you the code for normalized text. So normalized text looks like this. Takes a chat message, returns the sender and text. Sender is just copied as is. Text, we first replace any non-letter characters with a space. So non-letter is just, this is Unicode for anything that is not a letter. It includes like Greek alphabet, Chinese letters, whatever I count. Trimmed and lowercased. So for instance, if I were to, and by the way, you guys are welcome to send messages if you want to see how this works, but I'll just do one. Like, for instance, if I do something with, let me try doing something with emojis and lots of caps. So let's do, I see if I do like a Kotlin rocks with a rocket emoji in between and a banks, you'll notice after normalizing, it gets lowercase and then the rocket became a space. The banks became a space and it got truncated because of the trim. Next step is to split that text into words. And for that, we use a flat map. Specifically a flat map concat because we care about the ordering. And you will see, I was going to say Kotlin rocks, but I guess rock is fine. You'll see that it splits. It's a simple thing that splits each text into multiple messages, which is why we're using a flat map. And the code looks like this. So split into word looks like this. It takes a sender and text and returns a flow of sender and word. Where it takes the text, splits it using spaces, create sender and word from the original sender and the word. I reverse it, and there's a reason I reverse it, but it's not really necessary, but it just works better for my example. And then convert the collection to a flow, and you can see there's a extension function that for you to convert collections into flows if you need to, as we do here. Yeah, so that's what this is. So again, you're welcome to, if you want to just type in stuff, you want to see how this works, like if you want to, or even if you want to try to break it, that's fine. Hopefully it doesn't happen, but cool.
Yes.
Yep. It is very similar. It's not exactly like Java 8 streaming. I don't think it's quite reactive, but like if you're using like RX Java, it is. RX Java is basically Java's version of functional reactive programming. So next thing I want to talk about is filtering. So filtering, I'll show you the code so that you don't have to try and guess what it's doing. It takes the word and returns a Boolean if it's valid, and a word is valid if it's between min and max length. Min is a configurable value is 3, max is 15. And it is not part of stop words. And stop words, if you're not familiar, it comes from like NLP, natural language processing. And the idea is there are certain English words that are just uninteresting, right? Like the, or is, and like the conjunctions and whatnot. I'm not that familiar with grammar. So those tend to be uninteresting words in the English language. And then this is English based. Obviously, if I was doing it for German, I'll have a different list of stop words. And I get rid of them. So for instance, if I were to do something like is functional and reactive, you will see that is filtered out because it's too short. Only 3-letter words are allowed. And it would probably be a stop word as well. Functional is okay. And is three letters, so it should be valid, but it's a stop word. So it got filtered out. And reactive is valid. Next is where it starts to get more interesting. And so this is the running fall I was telling you about earlier, where we are using as the initial value something more complicated, in this case, a map. So for this, before I show you the code, I'll try and describe what it is. The function we have is update words for sender. So like I said, we are interested in only the latest 3 words for each person. This is so that, if you type something and there's typo, or you change your mind about where, you can always type new words to evict the older words. So what this is, the map is a map. It's actually the map you see on the right here. It's a map of string to list of strings, where the key is the sender, and the list of strings, the value is the list of the latest 3 words that we are interested in. The function is implemented like this. It's not too bad, but so this is the accumulator value. So this is the words by sender. So the map of senders to words. And it takes a sender word on each iteration, on each combination. So first thing it does is it gets all words for given the given user, right? For the current user, the user is currently processing. By doing words by sender, it gets the sender word.sender, which may be null because this could be the first word that the person is sending in. And if that's the case, it just returns an empty list. So the old word could be, the sender's current words, or if nothing, then empty list. New words takes the word, the current word that the sender just sent, and then prepend it to the list of all words. Distinct because we don't want a user to send the same word multiple times. And then take max words per sender, which is in this case configured to 3. So just keep only the latest 3 words. And then it returns a map that is the old map plus this new sender to the new set of words. Oh yeah, okay. I was wondering why my word became the most recent, but I did type something later. So I can show you, for instance, like right now, my words are functional reactive Kotlin. So if I type in, for instance, distributed, it will add distributed to the list, and you'll notice distributed is now the most recent one, and it kicked out Kotlin, is no longer there. Right. And then the next thing we need to do, because we to draw the word cloud, we are interested in the words and how many people sent in that word. And so that is where you count the number of senders for each word. And you do that by applying a map function to it. This, I think, is actually probably it's not that long, but it's probably the hardest code to read. But hopefully it's not too bad. It takes the input, which is the words by sender, the map from the key, where the key is the sender and the value is the list of words. Flat map the map, and take the value, which is the list of words, map it into a word to it.key, recall is the sender. right? Because this is the outer map where the key is the sender. So on line 4, the output of that line is a collection of, it's flipped, and it's words to sender, where sender can be repeated. Keep in mind, it is a list of pairs, so a sender can be repeated. And then we group by the left side. Oh, and keep, okay, and not just only can the sender be repeated, the word can be repeated too, because it, it is a list of pairs. So like in this example, oh, we don't actually have, let me just do one where I just type a word that someone else typed. So coroutines from Ian, right? So coroutines is now 2. So here you'll have coroutine showing up twice, where the key is coroutine and the value is me and Ian. Group by groups by the word, so coroutines, and it will group the second value. So what ends up here is you have a map where the key is the word and the value is a list of people who voted for that word. So each of these will have just one element, but then coroutines will have me and Ian, and the rest will have, one of us. But we are not really interested in the individual people. We are only interested in the count. So we do a final map value that just says, I'm only interested in the size of the value list. Yeah, hopefully that makes sense. And so this is what you end up with. And so you now have coroutines with 2 senders and then a bunch of other words with 1 sender each. So in terms of the flow, this is pretty much it, right? And so let's just show, a bird's eye view of it. So if you compose it all together, you start with the chat messages, normalize it by, lowercasing and removing non-letter characters, splitting it into individual words, filtering out words that are not interesting or too long or too short, collect the words for each sender, the latest 3 words, and then tabulate them by counting them up. And the code is actually really simple here at this point, because you're really chaining all those operations together. And so you start with chat messages, you map and normalize the text, flat map concat, splitting them into words, you filter it, you update the words for each sender. That's what the running fold is. Count the words. And 2 extra steps I want to mention. So the map colon counts, really it just takes, because the output of this is a map of word to counts, but I want to be able to convert it to a prettier JSON. So I'm wrapping it inside a data class, so that instead of just the map being at the top level, it's actually a field on a single object. That's really the only reason this thing exists. And then sharing, I mentioned earlier, is so that we are, if multiple people are subscribing to this flow, you are not performing this calculation multiple times. Cool, I see. Yeah, so in just ascending functional, so now that we've got 2 of those now. And finally, so this is the flow part of the application, but obviously for the application to have a UI, you need to pipe it somewhere, basically. And in this case, I am exposing it as a WebSocket. This is not really what my code looks like, and I'll show you what it actually looks like, but this is just to make it fit in a slide to show you the basic naive implementation, what it would look like. So if you're familiar with Ktor, if not, like you have a routing in Ktor that defines the routes for your application server. In this case, I have a WebSocket route at the root path. And what it's doing is the word counts, and this is the word counts that I showed you earlier, where we've got the map, flat map, and whatnot. I am doing, in this case, I'm doing a sample of no more than 10 per second. So 1 every 100 milliseconds. And this is because, I mean, in this example, we are not expecting so much messages to come through, but imagine if this was a larger, like a Facebook scale thing where millions of people are sending words in. You don't want the WebSocket connection to be flooded, right? To be saturated, because there's so much message coming through. So you can do, so sample is another operator that I didn't really talk about, but it's useful to have. I convert it to a JSON. and then collect and call send on it, which basically sends it to the WebSocket client. I will share the code in case you guys want to look at it. I will share a link to the source repository in chat. Yeah, and finally, so if you visualize it based on count, this is what it looks like. So I think, yeah, so this is really the bulk of the presentation. If there are like 4 more slides where we talk about more interesting, I definitely want to cover topics that are maybe not specific to the basics of Flow. So if there's questions so far, I'm happy to take them right now, or we can go through the next 4 slides and cover more. We good? Okay, let's talk about a couple of more interesting, like maybe this is an interesting way of building applications, but you might ask why? Like why I really know how to build something like this. Why are we using functional reactive streaming? So one thing that I think is cool about it, now Flow doesn't come with distribution built in, so you have to do it yourself, but there are things like Flink, Spark streaming that are very functional reactive streaming like, but have distribution built in. But we're not talking about that. We're talking about Flow here. So, when you're doing a distributed deployment, that's how if you want to scale up an application, let's say to Facebook scale, again, we are talking about 6 users here. So we're not really concerned about that. But if we were thinking about millions of users, we may want to deploy this application on multiple machines so that we can get parallelism. The thing with streaming application is we need to realize when you split it out that way, the order of the message is not guaranteed across different machines. So within a single machine, yeah, the order is guaranteed, but across 2 machines, one machine can be processing things faster than the other, so you cannot guarantee order. The consequence of that is that if you have a stream where the ordering doesn't matter at all, like you don't really care, it can be, can come about in reverse or random order, then the application becomes really easy to distribute. And this is true, I think, of things like ETL jobs where you've got, for instance, like Kafka or Kinesis stream of events coming in, and they typically come timestamped. And you really don't care if 1 or 2 records get flipped. You kind of just want to write it into your data warehouse, like your Redshift or Snowflake or whatever. And when people are running queries, they'll probably have a where clause that's limiting by timestamp, or they'll order by timestamp anyway. So it'll get reordered anyway. So in that application, it's really easy to distribute the application. On the other hand, if you've got cases where the stream order matters across the entire stream, like no 2 messages can flip, then you really cannot. Yeah, you have a problem. You cannot really scale this way. You're probably going to find some beefier machine or something like that. But I think most applications are somewhere in between, where the order of the messages matter, but only within certain subgroups. And for our word cloud application, I will show you one of this. So I'm actually going to show you an example. So I want to show you, first of all, that the message, some of this message can be reordered, but I'm going to send some things. And Ian, if I could get you to send some messages while I'm sending, I'm going to send 5 messages. And in between, if you can type in whatever you want, like in between, like 1 or 2 messages, it doesn't really matter. But I'm going to just type in 1 right now. Sure. And if you want to type 1, and I'm going to do something just really funny so that. And I'll just do the next 3 because I think I've got enough to. Right, let's just say if I typed in everybody hates functional reactive streaming. In this case, you'll see that order matters amongst my words, right? You'll see that on the, I know this is a bit small and hard to read, but hopefully you can kind of make up the words at least. That my words are, oh wait. Oh, I think it got confused and thought that Ian said, okay, looks like we found a bug. But anyway, so my words are like functional, streaming, reactive. And everybody hates got dropped off because those are not the last 3 words. But
Right.
that's because the order was maintained amongst my words. Right? We cannot, if they were processed in reverse, then it would be everybody hates functional are my words. And we don't want that. However, if you think about it though, so order matters amongst my words and order matters amongst Ian's words. But between mine and Ian's words, like if Ian's words all got processed before mine, or they all get processed after mine, it doesn't matter.
Okay.
Right. And the point I'm trying to demonstrate here, and I actually use colors here for that purpose, and that's kind of why I asked Ian to demonstrate, because I knew he had a different color tile. The idea is we can partition data this way based on the sender, because order matters for a specific sender. So this means we can take all the, I don't think we saw any green tiles, right? Yeah, unfortunately, there were no green. Green is another color that can show up, but I don't think any one of us ended up in a green partition. But the thing I was trying to show is we can split, if we were to split into multiple nodes, we can have one node process all the orange ones, one node process all the blue ones, and one node process all the green ones. And we can do that while still maintaining order for each user. And so we can scale without losing the order guarantees on a user level, because we don't care, for instance, if Ian's messages all get processed before mine or after, because that doesn't matter. So if like Ian's node runs faster than mine or slower, it doesn't matter as long as each user's messages gets processed in order. Right. So that's one thing I wanted to talk about. And the other one that's more interesting, but like kind of a mind bender in my opinion, at least the first time I've learned about it, is like, what should we use as the source of truth for an application like this? And keep in mind, when I say source of truth, I don't necessarily mean the persistent data structure that is easy to query, but more the thing that you are able to build application state from. And let me try and at least give you more examples, right? So let me just like go through the slide, right? So I think initially we may think, like, if we were to build a system like this, and you want to build it so that you can restart the application without losing data, you might think that the user to words map would be the right thing to put in the database. And I think it ultimately is. Because if you think about it, if you store that to the database when you restart your application, you will have all the information you need to pick up where you left off. Like if you store it after that, where you store only the words and the counts, you may not have enough information to pick up where you left off, because like you start up and then let's say Jack sends in functional, and you know that functional already exists, but you don't really know if you should increment it, because you do not know if Jack maybe has already sent functional in the past. If it's already one of his words, then it should really just get reordered and it doesn't really increment it. Also, there's also the question of, okay, maybe Jack, you want to accept Jack's functional, but do you need to remove one word, because maybe Jack has already had 3 words and we need to kick something off. And if you just keep the counts, that's not enough information to restore that. But if you store the person to words list in like a Postgres table, you will have enough information to at least pick up where you left off on restart. The thing though is, what if you want to make certain changes that are more, that maybe people don't think about, like what if instead of just keeping each sender's last 3 words, you want last 7 words? Like even if you just store that the Postgres thing that I just mentioned, like the person to words list, you really do not have enough information to do that. And granted, you could argue most people wouldn't want to do that, but if you wanted to, so this is something to think about. Or if you want to add or remove stop words, you really would not have enough information to rebuild state by doing that. And so the idea here is an idea of event sourcing, which is to say that the source of truth of your application should be the source events. Like you should keep and this is why I use Kafka as in my example, is that you should store those original chat messages as your source of truth. Now, it is not going to be the most performant data structure to query. It will be slow each time you restart if you have to like replay everything. So you do want to keep that Postgres database, but it's a good idea to keep the original stream of data as well. And that's what event sourcing is. And again, I'll come back to this. And I want to show you again. I'll just describe it. Why this I think is a good idea. At least the way I think about it is because as you flow as your data flows through your application, you're actually like losing information, right? Like when you at the beginning, you actually have the sender and the recipient and the text with capitalization and emojis and whatnot. After the first step, you basically forgot who the recipient is. You don't need it, but you know what if you change your mind later and you decide you need it after all? If you don't persist it, you don't have it anymore. Similarly, you will have like words like I guess I don't have it here anymore, but like the original form where it's capitalized and there may be emojis. But that information is lost after the second step. So if you don't keep this, you only keep this step onward, you've already lost some information. And you'll notice each step of the way you are losing a little bit of information. So the idea of event sourcing is you keep the thing on the left forever, even though you may not use it for the application. So if you decide in the future you want to tweak something, you have that information to play back. And I think I've been watching videos on event sourcing. Another idea is if you want to build your staging environment with production data, you can use the events to play it back into your database or whatever. So I want to show you an example of exactly one of the things I said, right? What if you decided that instead of just the last 3 words, you want to keep each user's last 7 words? And so this is an actual application that's running. So I'm going to show you. So the application is running here. I'll show you the code in detail just to show you that that there are no tricks. That the code that you saw on the slides are actual code running. But I did make it configurable. So I've got my word cloud, and max words per sender is set to 3 right now. Let's say I set it to 7. Actually, before we do that, because this screen is going to reload, I will just kind of remember, like, so functional, there are 2 functionals, 1 streaming. I will say, and if one of you wants to take a screen cap so that you can refer back to it, that's fine. But like my words are functional, streaming, reactive, and Ian's are functional encapsulation threads. So we'll just pick a couple of points to remember. So now I changed it to 7. I'm going to restart the server. Did the click register? I thought it did, but maybe it didn't. So it shut down, it restarted, and you'll notice that we are back to blank state. And it actually, like, I'm not sure why, but it can take up to 2-3 minutes for the application to replay from Kafka, which, I mean, it's not a lot of message. I don't think it's slow. I think maybe it's just that's just a delay where it waits. It doesn't process the data right away. But while we wait, and I believe this is the real last slide. So if there's any questions, I'm happy to take questions now. But otherwise, we can wait for the data to load, and I'm happy to go through the code. Okay, here we go. Right, so now without having to ask all of you to type all your words all over again, it's able to just replay all these words. And you'll notice this time that there are, oh yeah, my hate is back, but there are 7 words for each user. So my list of words are much bigger. Ian's list of words are bigger too. Right. So again, this is like something called event sourcing. And the thing is, if you now, I'm not saying go do event sourcing right now. It's an interesting idea. Learn about it, because what I've learned watching YouTube videos is, yeah, it's a cool idea, but it also has some, you need to know what you're doing. because there are certain things where your data could get out of sync, like or there could be delays. Like eventual consistency has to be okay, especially if you are doing event sourcing to multiple. Like in my case, I'm just saying there's only one Postgres, but if there are multiple different downstream data sources that you're doing snapshots on, they could get out of sync briefly before they catch up again. So something to think about. One last thing I want to show you, I just realized for event sourcing, I think we're done. Let me make sure it's the last slide. Oh yeah, we're back to this. Okay, ask the question. One last thing I want to show you that is also event sourcing related, though this is not really a Kotlin Flow thing, but this is because my slides are actually wrote as a web app in Elm, and Elm is another tool that I'm not sure if you'd consider it functional reactive streaming, but it's definitely functional, it's definitely reactive. The streaming part is the part I'm not as certain about. The cool thing about Elm is, let me try and do this. It actually it is event driven, so it's message driven. It keeps track of all the events. So these are all the events that you see on the right are all the events that as I was presenting, as I was going to the next slide and next slide. That's why you're seeing the next, and then you'll see event. This is basically information coming from the server. But because Elm is effectively functional reactive streaming based, I'm able to go back in time. I'm able to I'm just clicking up on this list here, and I can show you, I'm basically able to rewind time and show you one by one as the messages slowly disappear. So, I think this is a cool example of what you could accomplish with event sourcing, in this case, using the Elm debugger. I think I'm really done this time. So if anyone has questions on or off camera, and if you guys want to look at code, we can do that too.
You answered some of my questions there at the end, so that was great. I was curious how the slides are implemented. But I did have another one you didn't get to, which is how are errors handled, and then how is debugging? Did you have to do any debugging, and how's the tooling around debugging these flows working these days?
That's a good question. I don't have a lot of experience with debugging, so I cannot say with certainty. I know probably within a function you can probably add a breakpoint. But yeah, that's a good question. I actually do not know. I don't really I kept this. One good thing is I kept the flow simple enough that I was able to implement it relatively easily. And it's kind of like the debugging I did is, oh, the data is wrong. Let's try and figure out, because it's functional, I can relatively easily reason about what it is. In terms of error handling, I know you should, in general, I do it again, follow functional programming best practices, which is I avoid using exceptions, because I believe if you do an exception, it will just cause your whole flow to terminate. So if there's something that can fail, do something like return a result type. I'm talking about Kotlin's result type, which can be a success or an error. You could use the arrow variant of it. I think other libraries have a result type, I think they call it a discriminated union. Or you could also, even as simple as, if you don't care about what the actual error is, just that an error occurred, you can just return null. So if a map, I think I showed you one of the operators in Kotlin is map or null. Oh, sorry, no, map not null. Right. So this basically takes a function that returns something that's nullable. So for instance, if you convert an integer, or let's just say you're converting a string to an integer by parsing it, you can do a map not null, and you take a function that attempts to parse a string into an integer, but if the string does not represent a valid number, just return null. And then map not null will just say, okay, that means you don't care about the strings that are not valid integers. So that's one way of doing it. Another, obviously, you return a result and you persist the exception so that you can log it or, report it into your metric system.
Yeah, it's interesting. I think like a lot of the, I'm thinking about the kinds of exceptions you could get that you really can't anticipate, like out of memory, for example, or things like that. And I'm imagining something like a famous or infamous Ticketmaster kind of like thing where you're really dealing with like huge load, and it's really important the ordering. And it's, as I think about the event sourcing you did, this event sourcing just kind of solved all those problems. As long as you're capturing the events, if the whole thing crashes, you can kind of recover and replay.
Yeah, that's
So
why I think it's
even
really
because you're not
cool.
going to have like a a union return type, an either or a null for like an out of memory error, right? Or there's all kinds of things that happen on the JVM platform or other platforms that you're not supposed to catch,
Yeah,
because they
yeah.
basically mean game over, man. Shut this process down and restart it. The event sourcing, if you've got an event source external to that process, solves the problem of recovery. Pretty neat.
Yep. Yep, it's really cool, and I really want to learn more about it. Like at work we use Kinesis instead of Kafka, and we use a lot of things where I think we could benefit from event sourcing, but we don't really do that. So yeah,
Same here.
yeah.
Yeah,
It's
interesting.
it's a cool thing that I'd like to explore more.
So a lot of this seems you mentioned a little bit about remoting with perhaps like Ktor, but it seems like you said that the Flow API is really a local API. So I can't recall, what were the other technologies, and have you thought much about how you do remoting of these flows as they get bigger and more complicated?
Remoting like HTTP calls, for instance.
Well, just distribution,
Oh,
right?
distributing
You
it.
have,
Yeah.
yeah, distributing it.
Yeah, I think in Flow you could do it yourself, but I feel like it's a little bit weird. So I didn't try to. I guess I could have made it a part of the demo, but I was thinking like instead of one application that goes from chat messages all the way to the word counts, maybe I can break it up so that up until I would think maybe the words per person can be the application, and I can distribute. I can have, like I said, like three deployments, one doing the orange values, and one doing the blue, and one doing the green.
Mm-hmm.
And then they all, like, I'm thinking maybe feed it into another Kafka topic and a separate application where order needs to matter, but at the same time load is hopefully lower by now, read from the Kafka topic. So that is one way of doing it if doing in Flow, but I don't think Flow really does a lot to help you in that area other than to help you think about your program and break it up. Other tools that I think have remoting or distribution built in are like Apache Flink. I'm not sure if you heard of it, and I believe Apache Flink, the way you write Apache Flink applications is similar to functional reactive streaming, right? So maps, flat maps, and whatnot. Like they may not be exactly that, but similar enough that if you know Flow, you probably will be able to get your way around an Apache Flink application. And another well-known one is Spark Streaming. Though with Spark Streaming, as I understand it, it's not so much real-time processing, but they call it like micro batching, because Spark is ultimately a batch data operator. So it will read from Kafka, but it tries to read up to, I don't know, like whatever small batches, right? Micro batches, which is configurable. Like it processes 1,000 at a time, for instance, so that it kind of simulates streaming while it still has it's still optimized for processing batches of data at a given time. But yeah, good questions. Like Flink and Apache's Spark are the only two I'm familiar with, but I'm sure there are others. I know Flink superseded Storm. So before Flink, there was Storm, and we used Storm at one of my previous jobs. We never switched over to Flink.
I know like RSocket is a reactive, you mentioned back pressure, right? It's just sort of inherent in flows. And so then if you're going to remote a flow, don't you want to preserve that? And I believe RSocket is a messaging remoting protocol that does support back pressure, but I don't know if anyone's written a flow to RSocket, connector of any kind.
I bet there is if you look.
Yeah.
It may not be
Yeah,
battle
maybe.
tested
Yeah.
though, but I bet someone has
Right.
tried to. Like the Kafka one I found was like, it's not part of the library. It's someone else had written it. So, but yeah, how reliable it is another question. And maybe you might want to write it yourself. But back pressure is an interesting thing, especially like now if it's like a flow like the one I showed you where it's just integers counting up, that's relatively easy to do. You kind of just, okay, don't count it until I need it. But there's also things like, what if you're gathering data from, like, let's say your tweets, right? Like tweeters, like the data is there whether you're processing, you're able to keep up or not. And I think that's where you need to be okay with dropping some data on the floor. And I think that's where
you did that you had there. The sample. You had the sample operator there, I think.
Yeah. And that's where it's okay to drop it because you're really not losing information. You're still getting the latest counts. But sometimes you may not be okay, and hopefully you are. And I think that's where things like functional reactive streaming with back pressure like gives you options on how you want to handle it. And I think that there are things like typically the way it's done is buffer up to a point, right? Like if you've got enough memory to buffer this, buffer as much as you can. But configurations I've seen is, okay, once your buffer fills up and you need to start dropping stuff, you need to decide, do you want to drop the earliest stuff because the freshness of the data is more important? Or do you want to drop the latest stuff because you want to have, I'm not really sure what the use case would be, but you want to have, all the data you've collected. And so everything new
or random for fairness, right? You want a fairness approach where it's random what gets dropped. And interesting. Yeah. I see we have a question in the chat too. I don't know if the chat gets into the recording, so I could read it out loud. It says, instead of classifying operators into ending and continuing based on naming conventions or implementation details, what if we have suspend, resume, finish methods, extensions, /extensions on all operators?
I am having a hard time following. So, is the question, instead of classifying it to ending or continuing, so is this like the terminal versus non-terminal?
I think so. It might be that, there's nothing in the naming conventions that tell you whether an operator is terminal or not. You just kind of have to look it up in the API or memorize them over time. So
got it.
A suggestion to, for naming conventions, right?
No, that's a good idea. That's I guess that's just not what they did. That's certainly not what Kotlin Flow did, but I don't think anyone does that. And I think it's just because the naming is, I guess they just expect you to memorize it, and hopefully the name kind of makes sense based on context, in the sense that like if you're thinking about it from a collections perspective, like you kind of know when you do a map, if the input is a collection, the output is also a collection. And so when it's something like that, it'll be a flow to flow, and that is non-terminal. Whereas if you're doing like a reduce or fold, you're really getting a single element, or you're folding it down into a single element, and the output is no longer a collection or no longer a flow. But I mean that's a thought, right? Like where, and I do not know if there may be libraries that do that, where they name it in such a way that you don't have to think about a terminal versus non-terminal thing, and it's kind of just in the name. But that's a good thought.
I can say it's not the first time I've ever heard the question for people who are, and including myself, learning the functional programming paradigm. Like, why are all these things named so unintuitively? For those who are new to the domain and the space, and I think you even called out there was scan, and they renamed it to what did they?
The running fold,
running fold, right? Because even in that case, there was a concession to, what does this even mean?
Yep. No, I agree. And like this is actually a good point, because like I did like write this was in Swift, I think, but reactive streaming application. And I knew I needed something like a fold, but I wasn't even thinking about the terminal versus non-terminal. And I was processing, and this is what I said, right? Where sometimes when you do a fold on an infinite list, you may just end up waiting forever. And that's exactly what I did. I folded on an infinite list. I think it was like stock prices, and I forgot what I was doing with it. But I was actually expecting to do a running fold, but I did a fold instead, and I was like wondering, my program isn't crashing, but then I'm also not seeing outputs, and like, what's going on? Then I realized, oh wait, that's right, because fold basically needs to wait for the whole thing to run, and then produces just one element, and then that's when I realized, okay, I need to do a scan here. It is, I think, unfortunately, there is no good answer from I think it'll be easier to pick up, but I think it's one of those things where with experience, you kind of realize, and also, you know what to look for in the API documentation. You can see that, okay, if this thing returns a flow, it will keep going if it doesn't return a flow. And also, I would say, for the most part, there are a handful, like maybe 5 or 6 terminal operators. So collect is the most generic one. First, last, reduce, fold. And so if you just memorize those, and I think maybe a couple more, that's basically, then everything else are non-terminal. But yeah. But yeah, so the next question is, but flows can be finite, right? So why make the distinction? I think make the purpose of making the distinction is because like, I would say the distinction was maybe I called it out, rather than, like, I don't think the documentation like makes a big deal about it. It's more I called it out because I feel like it's important to realize that what it means, right? Like, if it's a non-terminal operation, it is typically not a suspending operation, and so you can call it from wherever. You don't have to worry about, I'm calling it, but oh, I'm not in a suspending context, and I need to figure it out. And I felt like it's useful to know.
I'm not sure if this answers the question, but I think part of it also has to do with flows versus flows, which are streams, versus collections, which collections are defined and known ahead of time, whereas the whole purpose of a stream is to only have like sort of one active unit or element of the overall collection at a time. And therefore, the ability, say, to count ahead of and know all the parameters. You may not even know that the flow is, or the stream is finite or not, until the last element arises and it says, okay, now I'm done. Whereas with a list, you know, okay, this list has 20 elements, and now that I'm on number 20, that's going to be the end. So I think that might be right. Yeah, I think that's, yeah. I don't know the answer to what you're asking, but yes, that's certainly a valid question. Like, yeah, how would you do that? That's interesting.
Cool. What else?
Yeah, I see another question. No, I was gonna ask, do you think we should stop recording and
Sure.
go make it a
Yeah. I figured I'd see if anyone else had anything else they thought would be good for the general audience, and if not, then we'll call it.
I'll make a comment that I think it's okay to be public, and I think this is really great because there is a lot of desire. There's a lot of attraction of, again, having a reactive based system, which essentially is saying, like, the state of my application or my application is a function of its state. You know, that's the whole paradigm of React. This is you know, essentially universal, whereas wherever these flows are coming from, wherever these flows are being generated from, whether it's user input, whether it's your database, whether it is incoming HTTP requests, whatever they happen to be, every time something comes in, instead of my application having to, you know, take these steps or perform a function, it's essentially like reacting to that. And yeah, you can see how it would be like an attractive thing. So I think the way you did, and the word cloud is a great example of that. Like, hey, you don't know how many words people are going to enter. You don't know how many people are going to be in the chat. You don't know any of those things. But every time it gets updated, it's like automatic. Yeah, these functions get called technically, but sort of the way of architecting the application is to like, okay, when something comes in, it handles it automatically, as opposed to like the application having to like go here, do this, do that, and then return, you know, a new thing. So yeah, it's
On-demand processing.
yeah, essentially, right. And you are seeing, especially in the database, you know, you have JDBC, you've had that forever. Now you're starting to see this R2 DBC, which is reactive based, you know, database querying or sort of event based updates to your database, you know, which you know, works in alignment here. So I definitely think, you know, yeah, you'll start to see applications being built this way. I think a little bit more. Like you said, it's not perfect for every use case, and there's a lot to get your head around. It's exactly what you said, errors and stuff. But yeah, no, this was great. Very cool.
Cool. Thank you. I'm glad you liked it. It was fun. It was fun coming out with the idea of doing it and trying to figure out how to visualize all the things.
Right.
So
Right. I mean, I'm fortunate. I think probably most people here are, you know, that I have some knowledge, messed around back in the day with RX Java and stuff. So it can, you know, I'm not totally in the dark here, but yeah, it helps me follow along. But having it native to Kotlin, having the flows, yeah, I think it makes it more attractive. Yeah.
Excellent. Well, unless anyone has any other questions, we'll end it with a big thank you to Jack. Really appreciate the talk. It was very interesting and kind of cool things happening with Kotlin all the time. Thank you, sir.
Thank you. Thanks for having me. Appreciate it.